In this video, we'll be going over problem of the week number 6. So let's start with part A, or the only question we have. Here, you're trying to determine if the given series are convergent or divergent. In this question, there is several tests you can use, but probably the easiest one to use is the integral test. Here, f of x will be equals to x squared over x cubed plus 1, and you can see that this is positive, so that's a requirement for the integral test. So you have to integrate from 1 to infinity x squared over x cubed plus 1. We need a substitution. Let's say u is x cubed plus 1, then the u is 3x squared dx. So then this becomes the integral of 1 over 3 du over u, which is 1 over 3rd ln of u, which is 1 over 3rd ln of x cubed plus 1, and this will go from 1 to infinity. Remember, this requires that you actually use limits, but it will be 1/3 times infinity minus ln of 2, so therefore this is infinite. So that implies the integral is divergent, so that implies that the series is divergent by the integral test. And that's it. In part B, there is also several ways to the problem, but again, probably the easiest one is to use the limit comparison test. Not the comparison test, but the limit comparison test. So here we have that an will be tangent inverse. And when I compare this with 1 over n, or the harmonic series, remember we already know that this thing is divergent, so just keep that in mind. So according to the limit comparison test, you take the limit as n goes to infinity of the ratio. Okay, so on the top, the limit is 0, and on the bottom is also 0, which means you can use L'Hopital's rule. So by L'Hopital's rule, this is the limit now as n goes to infinity of the derivative of the top divided by the derivative of the bottom. The derivative of the bottom is going to be minus 1 over n squared. And recall that the derivative of tangent inverse is 1 over 1 plus the argument square times the derivative of the inside, which in this case is again negative 1 over n squared. That's the derivative of this part. Here these two will cancel, so this will be the limit as n goes to infinity, 1 over 1 plus 1 over n squared. Well, notice that when n goes to infinity, this thing goes to 0. So this is the same thing as just the limit as n goes to infinity, 1 plus 0. So this is just 1. So if you get a limit that is a finite number, which is what we got here, then the limit comparison test says that both of them either converge or diverge. In this case, since this one, and by this one I mean b of n is divergent, that implies both of them are divergent. Hence our series is divergent. Okay. In part C, because of the exponents right here are powers of n, The most appropriate test to use is the root test. You can also use the ratio test, but let's go with the root test. If we use the root test, remember we're going to take the limit as n goes to infinity of the n root of the absolute value of a to the n. And we're trying to see if the limit is equals to 1, more than 1, or less than 1. First, let's start with what's the absolute value of a to the n. If we take the absolute value of this, then you end up with just phi to the 2n over n squared to the 9 to the n. Then if you apply the n root of that, it's the same thing as multiplying by 1 to the n. So remember, this gives you phi squared, because the n will cancel, and on the bottom this will be n to the 2 over n times 9, because the n cancel. So then, if we take the limit, it's the same thing as the limit as n goes to infinity of phi squared, which is 25, divided by n to the 2 over n times 9. Now recall that the limit as n goes to infinity of n to any constant of the n is equals to 1, again using L'Hopital's rule. So in our case, the limit is phi squared over 9, which is 25 over 9. This is more than 1. So that implies that the series is divergent because of the root test. Now in part D, the best method to use, since this one has a factorial, is the ratio test. So we use the ratio test. This is what we have here. an is n to the n over 4 to the n times n factorial. So that implies that a of n plus 1 is n plus 1 to the n plus 1 divided by 4 to the n plus 1 times n plus 1 factorial. You can simplify this a bit more to n plus 1 to the n times n plus 1, and on the bottom this is 4 to the n times 4, and this is n plus 1 times n factorial. This part gives you this. So far you can cancel this and this. Now let's take the ratio, and remember the ratio test, you had to divide these two, take the absolute value, which in this case is not necessary. We have n plus 1 to the n over 4n times 4 times n factorial, that's a of n plus 1, times a to the n, which will be 4 to the n factorial, n to the n. The n factorial cancels this, 4 to the n cancels this, so you end up with 1/4 n plus 1 to the n over n to the n, which simplifies to n plus 1 over n to the n power, which simplifies to 1 to n to the n. The only reason why we simplify that is because recall that the limit as n goes to infinity of 1 plus 1 to the n power is equals to e. So hence, in our case, the limit as n goes to infinity of the ratio is equals to the limit as n goes to infinity of 1/4 times 1 plus 1 to the n power, and remember this is 1/4 times e, which is less than 1, since e is around 2.7. Since the limit is less than 1, that implies that the series is convergent by the ratio test. In part E, you have several choices. You can use the ratio test, the root test, and the integral test. The easiest one here is probably the ratio test. So here we have an is n e to the minus n, which is the same thing as n over e to the n. So hence, if we take the n root of the absolute value, it will be n to the 1 over n over e. Then the limit as n goes to infinity of the root is the same thing as the limit as n goes to infinity on n to the 1 over n over e. Recall that the limit as n goes to infinity of n to 1 over n is just equals to 1 by L'Hopital's rule. So therefore this is 1 over e, which is less than 1. So that implies that this is convergent by the root test. Remember, you can also use the integral test here. It will take a little longer, or you can use the ratio test too. Should be pretty fast too. Part F looks like a geometric series, and we have to check. Notice that 4 times negative 1, 4 gives you negative 1, and negative 1 times negative 1, 4 gives you 1, 4. So therefore this is a geometric series. So this is geometric. R is equals to negative 1, 4. The absolute value of R is less than 1, so that implies that the series is convergent because it's a geometric series. That's it. In part G, the best method to use is the comparison test. So let's start like this. Notice that obviously n squared is equals to n squared, right? So if we add 1 to this, obviously it will be greater than n squared. Also, if you take the square root on both sides, that means n squared plus 1, the square root of n plus 1 should be greater than n. If we multiply both sides by n, then that means that n times the square root of n squared plus 1 has to be greater than n squared. Okay? Also, recall from basic math, if 4 is greater than 2, that means 1 over 4 is less than 1 over 2, right? So we use the same logic. Here we end up with 1 over n plus 1 has to be less than or equal, or it's actually less, but less than or equals to 1 over n squared. This is the original, this is an, and this is bn. Recall that this is a convergent series. Why? Because it's a p series where p is equals to 2, which is more than 1. So by the comparison test, since an is less than or equals to bn, so by the comparison test, and this one is convergent, that implies that our original series is convergent. And that's it. And the last one, part H, the method to use should be the ratio test because of the factorial. So here an is 1 over 2n plus 1 factorial. That means an plus 1 is going to be 1 over 2 n plus 1 plus 1 factorial. This is 1 over 2n plus 3 factorial. Excuse me. Which reduces to 1 over 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Remember that the n factorial by definition is n times n minus 1, n minus 2, and so forth until you get to 2 times 1. So hence the ratio is equals to 1 over 2n plus 3 to n plus 2 times 2n plus 1 factorial times 2n plus 1 factorial over 1. So this will cancel down. Then take the limit. So the limit as n goes to infinity of the ratio is equals to the limit as n goes to infinity of this, which clearly this is equals to 0, this is less than 1, so that implies this is convergent. It's actually absolute convergent by the ratio test. That's it.